Hello, everyone, and welcome to Talk Nerdy. Today is Monday, June 22nd, 2020, and I'm the host of the show, Cara Santa Maria. And before we dive into this week's episode, I want to thank those of you who continue to support the show. One of the best ways you can show your support is by visiting Patreon, patreon.com/talknerdy. You can learn more there. Or you can visit the Talk Nerdy store at talknerdymerch.com. And of course, if you're not in a financial position to support, which many of us aren't right now, you can just rate and review on Google Podcasts or Apple Podcasts, or you can just share on social media. Tell your friends. That really does help. You wouldn't believe it, but it does help. All right. This week, I want to thank the top Patreon subscribers, patrons, as I call you, Michael Gaucher, Mary Neva, Christopher Pitts, June Sapara, Pasquale Gelati, Ulrika Hagman, Dudas Infinitas, Brian Holden, Daniel Lang, and David J. E. Smith. Thank you all so very much. All right. What are we talking about today? Ooh, it's a good one. It's a really good one. Okay, so I had the opportunity to sit down with Dr. Valerie Trouet. She is a dendroclimatologist. That means that she studies the rings in trees to understand the climate of the past and also how it influences ecosystems and human history. She is an associate professor in the Laboratory of Tree Ring Research at the University of Arizona. And her recent book is called Tree Story, The History of the World Written in Rings. Oh my gosh, so fascinating. All right, so without any further ado, here she is, Dr. Valerie Trouet. Well, Valerie, thank you so much for joining me today.
Thank you very much for having me, Cara. It's an honor.
So I'm really excited to talk about a topic that we've really, in the 6 years that I've been doing this show, never gotten into. Now, we've talked about trees. We've talked about trees a lot on the show, but mostly from a purely ecological perspective and almost like a nature kind of enjoyment perspective. What can we learn from trees in the wild? What can we learn from deforestation, from habitat loss? But I've never ever sat down and talked about sort of the inner workings of a tree and what we can learn from the cross section of a tree. And you, of course, are an expert in tree rings.
I am, yeah. I'm a professor in my department is actually called the Laboratory of Tree Ring Research at the University of Arizona. So we have a whole department with about 12 faculty who all use tree rings to study how the world operates and has operated in the past.
That's amazing. And a blurb in your book, or at least the summary in the front jacket, refers to it as dendrochronology. Is that the proper name for what you study, or is that only like a portion of what you study?
That is a proper name. So dendrochronology comes from dendros, Greek for tree, and chronos, Greek for time. So it's the proper name. Dendrochronology is another word for tree ring research, for this use of those of us who use tree rings to study time, basically.
Mm-hmm.
And then personally, I am there's subdivision. So I am a dendroclimatologist. I use the rings in trees to study the climate of the past. But there are also dendroarchaeologists who use tree rings to study archaeology or art history. And then dendroecologists who primarily use tree rings to look at the history of forests. Dendropyrologists who use tree rings to study the wildfires of the past, and so forth. So there's a lot of subfields.
Yeah. So, I mean, and all of that is really kind of contained within the rings of these trees. I mean, I guess I always knew that there was some correlation between counting rings and knowing the age of a tree. But I figured that the science was a little more complicated than just 1, 2, 3, and that equates the years. How does it actually work? How do you count rings to know how old a tree is?
Yeah, so that's what you're describing is really one of the main reasons why I wanted to write this book, because many people as kids learned that by counting the rings in a tree, you can estimate its age
Mhm.
because every ring represents 1 year. And so the more rings you have, the older the tree. But there's not as many people who know that there's a whole field of science based on that concept and all of the scientific discoveries we've been able to make based on that concept. And so the counting of rings really is the basis of it, but not all rings are equally wide. That's, I guess, where we extract our information from. So, in a good year, when the tree is happy, it will grow a lot and it'll grow a wide ring. In a year when it's not so happy, it will not grow a lot and it will form a narrow ring. And
Mm.
so if you have a 500-year-old tree, and you take a sample from it, you'll see 500 rings in it, but they won't all be equally wide. So you'll get an idea over the past 500 years which ones were the years that she was happy and which ones it was not so happy. And whether a tree is happy or unhappy to a large extent depends on the climate under which it grows. So, for instance, in Arizona, where I live, trees like it when it's wet and they don't like it when it's dry. So, they will grow wide rings in wet years and narrow rings in dry years. And so, in that same 500-year-old tree, if you see wide rings, those were the wet years. If you see narrow rings, those were the dry years. And so all of a sudden you have a record of 500 years of climate of the past, not just 500 tree rings.
Wow, and I assume that that is contextual, like it's relative to the tree itself. Different species have obviously different widths and different looks to their tree rings.
Yeah. Yes, definitely. This is a simplified version that I was of how I explain things here. To be clear, we never base our analysis just on one tree. You
Mhm.
combine a lot of trees, and the you know let's say 20 trees that all grow in Tucson, Arizona, because they're all growing under the same climate, they will all be happy when it's wet and all be unhappy when it's dry. So the patterns in their tree rings will be similar. They'll grow wide rings in the same years and narrow rings in the same years. And so you can actually start putting those sequences of tree rings from different trees together and get better results that way. It's not the not species tree species is important,
Mm.
but it's not the main contributing factor. But you're right that the way the wood looks, the anatomy of the wood is quite different between species. And for instance, if you look at the tree ring sequences, and we call them chronologies, that have been developed across the world, and we have maybe about 4,000 of them now that are publicly available. The vast majority of those are from needle leaf trees, from conifers, because they have generally speaking, have much clearer rings. They have a
Oh,
simpler wood structure, and so much clearer rings, easier to read rings than uh, broadleaf trees.
interesting. That was kind of going to be my next question, which was, do all trees follow this basic pattern? Can you count age from the rings of every species of tree out there, or are there some that just don't really grow that way, or their rings just aren't very visible?
Yeah, so both of those are true. So
Hmm.
there's species that really don't have that grow a ring every year, but they're just not very visible because the differences between spring wood and the wood that's formed in the fall is not very clear. For instance,
Mhm.
aspen. They're very faint rings. They form a ring every year, but they're very faint and hard to distinguish. On the other hand, it's interesting how we started that, most people learned as kids that, trees form a ring every year and you can count those rings to know the age of a tree. That is true for most people in temperate regions. You
Okay.
ask people in tropical regions, they're not that familiar with that concept because a lot of tropical trees do not have that annual ring formation. Because really,
Huh.
what causes a ring to be annual is the seasonality in the climate. So when we have cold winters, that's when the trees stop growing. Or when you have very dry winters, the trees stop growing. But in the tropics, when it's always wet enough and always warm enough for trees to grow, and you don't even have that change in the day length between winter and summer, there's a lot of trees that actually don't form annual rings. They kind of keep growing throughout the year.
That's interesting. I guess maybe, yeah, because I grew up in Texas. A lot of us who grew up here in the United States are used to these, like, I guess, non-tropical, more like woody trees. Yeah, it's interesting that there's a fundamental difference there. I guess maybe if we backed up a little bit, it would be important to talk just in really simple terms about like what a tree ring is. Is it physically just that they add wood on to the outside of their trunk every single year?
Yeah.
I'm tr
So yeah. As I was explaining this, I realized I should back up. So you're right. Um, Trees have a stem, right? That's what
Mhm.
makes them trees. And the innermost ring is actually the oldest ring. And so
Okay.
everything that's wood is actually already dead material. So the only living part of the stem of a tree, so I'm not talking about the leaves or the roots, but of the stem of the tree, the only living part is a very thin layer of cells. We call that a cambium layer in between the bark and the wood. And
Oh,
so that,
interesting. So it's almost like our hair or our fingernails, like, we produce it, but there's only a little bit is actually what we consider to be,
yep,
like, connected to us or alive.
yep, that's a good way of putting it. And
Huh.
that also means, so from that cambium layer just under the bark, that's where the tree produces new wood in spring. So from the outside in, really, it starts putting on new wood cells. And so what makes an annual, why we can see rings in the trees is that the wood that a tree produces in the spring looks different from the wood that it produces in the fall. So in the spring, the tree has a lot of energy and it needs to transport a lot of water from its roots to its leaves to start growing its canopy. And so it forms big cells. And that visually, the wood that's formed in spring, we call it early wood because it's grown early in the season. The early wood is light in color. And as the growing season proceeds, as we're getting towards August, September, the end of the summer, the tree is now putting more energy in structure, so in making more solid wood rather than wood that can transport a lot of water. So towards the end of the growing season, what we call late wood, because it's formed late in the growing season, you get smaller cells with thicker cell walls because they need to be structurally more solid. Um,
Mhm.
and that results in a darker color. So every tree ring, every annual ring consists of early wood that's light in color, and then late wood that's dark in color. And then after formation of that late wood, that's when, in winter, the tree stops growing altogether. And then the next spring, it starts again with the light colored early wood. So really the ring boundary that you see is the difference between the dark colored late wood of one year and the light colored early wood of the next year.
Oh, I see. I'm looking at a picture of tree rings right now. Actually, it's in the cover of your book. And you're right. I see this very striking, almost zebra-like stripe to it, where it's this thin, light ring and then a much thicker, dark ring. And so the ring itself is actually that entire
Yeah.
region.
Yes.
Okay. So tell me, how does a tree actually make wood? I mean, I guess it's probably biochemically really complicated, so we don't have to get too into the quote, nitty gritty of it. But I think of an animal and how an animal moves, how an animal, utilizes energy, and it's very different than the way that plants utilize energy because plants, of course, don't have locomotion. They don't walk. They don't, they're not ambulatory.
Right. Right.
But plants do, you know physically grow larger. We see that. You plant a tree in your yard and, depending on the species, it can take decades, but it will grow larger.
Right. So we call it for trees, we call it primary growth versus secondary growth, where primary growth is growth in height, and secondary growth is growth in girth, so stem growth. So
Okay.
where the wood growth is the secondary growth, and in a way, trees are not unlike people in that they only grow in height up to a certain age, and then they only grow in girth anymore. So their secondary growth they do throughout their life. Every year they add on a little bit of extra wood. Some years they add on a lot of extra wood. Some years when it's not a very good year, it's not a lot of extra wood that they add on. But every year they grow in girth a little bit, and
Gotcha.
that's what we're measuring with tree rings.
And what about when they actually do grow in length? That's obviously not able to be directly measured historically, is it? Like you can't look at how tall a tree is and have this kind of same precise understanding of its lifespan.
You can have, depending on the species, you can have a bit of an estimate, but not really.
Okay.
Like I said, only up to a certain age, and then they stay constant. It's like people as well, just from looking at someone's age, you can tell whether they're a 5-year-old or a 20-year-old, but you can't tell whether they're a 20-year-old or a 50-year-old. Like after
Right.
20, they
Because
kind of
they're,
stay the
yeah,
same
kind of
height. So yeah.
stop growing. But trees just keep getting, I guess, fatter.
Exactly. Yeah, yeah, yeah.
And so when somebody, let's say, you're a homeowner and you have a tree whose root system is, busting up the sidewalk outside of your house, and it's recommended that this tree gets cut down. Sad, but it happens. So let's say that a tree gets cut down and now you have this giant log, you have a stump there, and you go over to marvel at the way that this stump looks. What can we really know from just looking if we were wearing your glasses, right? If I were looking through a scientist's eyes.
Well, I mean, first, like we said, you can see how old the tree was when it was cut down, more or less,
Hmm.
right? By counting its rings. Depending on where you live, you might see years when something odd happened. You could see maybe when an insect attacked the
Hmm.
tree in some year, not just nibbled a little bit on its leaves, but had a big uh, insect infestation that you will see in a ring, or maybe a big storm happened and it broke off a branch, and that year a big branch with a lot of leaves on it, or the storm blew off all the needles or leaves of the tree in a certain year, and that you will see in the ring of that year as well. Other than that, you will also kind of see that as you go from the center to the tree, and actually you can also see it on the cover of my book, as you go from the center of the tree towards the outer edges of the tree, the rings do generally get narrower. But
Hmm.
that's just a function of how of geometry, really. I mean, to put the same amount of wood around a small diameter will result in a wider ring than if the diameter you start with is already 3 feet, and then to put the same amount of wood around that 3 feet diameter, it will result in a very narrow ring
Right.
compared to if
Oh,
the
sure.
diameter is
That makes
only.
sense, right? It's just more surface area.
Exactly. So that we do have to work with that, but that's fairly easy to model, that effect of the diameter on ring width.
So when we talk about things like climate change or severe storms, fires, physical trauma, even disease, you can see the remnants of this within the rings of the tree. But my guess is that they show up differently. Like, what are some of these almost forensic clues that you're looking for? Because obviously, if it were as simple as count the rings, know the age, there it is, there wouldn't be an entire department. You wouldn't have a whole lab
Very
dedicated
true.
to
Very true.
this. So, yeah, I'd love to get into a little bit of like these different sort of things that you are trying to understand and what some of the indications or some of the physical manifestations of these things look like.
Sure. So there's two things. Like, one is we can look just at the width of each ring, regardless of whether there's anything special going on. But just by measuring the width of the ring, kind of what I explained at the beginning, will give us an idea of how wet or how dry it was, in Arizona, just by looking at the width of ring compared to previous and later rings.
Hmm.
Now, that's in Arizona. If, for instance, you go to the Alps or to Alaska or Canada, the trees don't really care how wet or dry it is because it's really dry enough most of the time. They care more about how warm or how cold the summers are. So they don't like it when it gets too cold in summer, and that's when they won't grow a lot. So
Gotcha.
there, if you look at trees in Canada or Alaska, rather than getting an idea of how dry or wet it was, they will give you an idea of how hot or cold it was. And so then by using trees from these high latitude or high elevation places, you can reconstruct temperature using that. But then to get back to what you were asking about, the various extreme events that can cause really changes in individual rings. Um, it really depends. One that I like a lot is they're called frost rings. They
Hmm.
happen, and there's a really beautiful photo of one in the book. Um, they happen when the tree already started growing, so it's, let's say, April or May, and then a late frost happens. That late frost will cause a disruption of the normal cell structure of the wood cells in the ring, and so they might burst the wood cells, and so you can see those kind of frost rings. Um, Not in all species, but in certain species. And so, what is cool, and that's also in the photo in the book, is that what causes like out of season frosts to happen. In the past, that was often volcanic eruptions. So we know that volcanoes, when big volcanoes erupt, they create cold conditions worldwide. And so, if a big volcano erupts, the chance of frost happening outside of the regular winter season is higher. And so, lo and behold, by looking at frost rings in some very old and high elevation trees, we've been able to line those up with past volcanic eruptions.
Oh, geez. So then, I mean, you know, I I guess something that's important to describe is how old some trees really can be, because you can in many ways look into the history of the tree to tell you things that either you're corroborating with written human history, or potentially we don't have a record of, but you can
Right,
make inferences from these trees.
right. So yeah, the oldest living tree on Earth is growing somewhere on the border between California and Nevada in the White Mountains. It's a
Okay.
bristlecone pine, and it's more than 5,000 years old. So it
What?
was 5,062 years old when it was sampled in 2012. And so at this point, it's very important, in case anyone is still in doubt, is that when we sample trees, we don't have to cut down these trees, right? We have a hollow core that's about a quarter of an inch in diameter that we core into the tree, and we can take a sample out of the tree that way. It's a bit like a biopsy. We don't need to cut
Okay.
down 5,000-year-old trees in order to be doing our science.
Whew, yeah. So this isn't just a function of like you find things that are already felled. You can take active live samples
Yep,
from
from
trees,
living
but you do
trees.
it precisely, like you
Yes.
excise a little tiny bit, and that doesn't like offend the tree at all.
No, because remember what I was saying earlier, that all the wood inside a stem is already dead, and the only
Yeah.
living layer is that very thin layer right under the bark. So from that layer, you only take a sample that's maybe half a quarter of an inch in diameter. So you're really not harming the tree at all.
Okay. Yeah. And does the tree itself, when it I guess this is a bigger question, and sorry to take a turn because I want to come back to this, but does the tree itself have some sort of reaction? Let's say when a biopsy, or I'm sure you don't call it a biopsy, but when a sample is taken, or, when something happens to it that's like a physical trauma, does it scar over? Does it have some
Yeah.
sort of, it does.
Yeah, that's a good question. It depends a little bit on the species, but typically, like, trees can't heal. Like, unlike
Okay.
us, they can just grow new wood and fill it up. Um, but they compartmentalize. So on the one hand, they um, exert chemicals around the wound to prohibit that any diseases come in or spread through the wood. On the
Hmm.
other hand, that when they form new rings, new wood, they try and close off that wound. So they will try and grow around it, over it.
Okay. Yeah, interesting. Okay. And so that probably also tells you something, right? When you're looking into those trees. So my assumption is that you can learn what you can learn at the microscopic level and maybe a little bit at the macroscopic level from these small core samples, but when you do look at a full cross section of a felled tree trunk, that you actually are going to learn a little bit more because you're going to see more geometry.
Yeah, definitely. Yeah. So with the core samples, you're getting an idea of what all happened.
Hmm.
With the whole stem cross section, you get much more information, obviously, and there are aspects, particularly what you were talking about in terms of wounds, that you cannot study with coring alone. For instance, if
Right.
you fire history, like if we look at wildfires of the past, if they have harmed a tree and wounded a tree, that kind of research you need to take a cross section. It's
Hmm.
impossible to do with cores alone. But even then, you don't need to. If you've got good chainsaw skills, you can actually take a wedge out of the tree.
Oh, wow.
Yeah, it's amazing how good some people are with a chainsaw. You can take a wedge out. So rather than cutting that down the tree, you take a wedge out of it, and that could be maybe only 10% of the surface of the tree, and it will still perfectly survive it. It's not a pretty sight, but it's doable.
All right, everyone, let's get back to the show. And so I guess tree ring researchers who look at different phenomena have slightly different ways that they study them. You mostly, as you mentioned at the very beginning, look at climate history. And so these cores are they mostly sufficient for the type of work that you do?
Yeah. For climate history, well, that's a good point. Yes. So coring, we definitely, for living trees when possible, and for climate, cores are very suitable. We core living trees, but then the thing is, we're not limited to only looking at living trees. We can
Right.
also make use of the wood of dead trees and of archaeological material and of historical buildings and even of, sub-fossil wood, so wood that was preserved in peat bogs or in riverbeds.
Huh.
But if the tree's no longer alive, we don't have to worry about killing it because it's already no longer alive.
Yeah.
So then, for instance, if you're taking a sample from a tree that's dead and lying on the ground, we prefer to take a sample with a chainsaw, because then you
Mhm.
get, as you mentioned earlier, you can get all the information out of it, and the tree's dead already anyway. So
And so, do trees, I guess you mentioned kind of archaeological or even like paleontological, kind of like fossilized, what we think of as petrified trees or petrified wood, or you also mentioned actual building materials in like old buildings that you can
right.
learn a little bit from that wood. If a tree just falls in the forest, haha, you haven't heard that one before. Does it starts to decompose, right? So at what point are you able to use dead tree material that hasn't been preserved?
Yeah, it's a good question. I mean, it's very interesting, and this is something I only learned from being a dendrochronologist, is that the rate at which trees that die in the forest decompose depends a lot on how warm or dry or moist it is in that forest.
Mhm.
So, in a rainforest in, let's say, Oregon or Washington, you're not going to find wood that's 100 years old, that has been lying around for 100 years. There's going to be very
Right.
severely decomposed. On the other hand, what I was talking about, those bristlecone pines, those 5,000-year-old trees that I was talking about, they
Mhm.
grow high in the mountains and in a very rocky area where it's and cold and very dry. So even when they die, they can. We have found, not me personally, but some of my colleagues have found tree trunks that have been lying around, of bristlecone pines, that have been lying around for more than 1,000 years. So they
Wow.
sampled them, and these trees died 1,000 years ago, and they're still on. They're still there, which is
Oh,
mind
gee.
blowing. And that allows you, if a tree died 1,000 years ago and it was 3,000 years old when it died, all of a sudden you can go even further back in time than before.
That's incredible. And so we're not just talking at a certain point, uh, weather patterns or wildfires or things like that. But my guess is that you're able to see things like glaciation, like changes in ice ages, things that you can then corroborate with evidence from, scientists who are taking ice core samples and who are looking at the polar caps and things of that nature.
We're getting there. We're getting there. We still have a lot of work ahead of us. The longest continuous tree ring chronology, so the
Hmm.
longest record for which we have one ring for each and every year right now, is 12,650 years old. So it's
Jeez.
just, yeah, it's just older than the last than the Holocene and the most recent interglacial. So that's based on wood from oaks and pines in Germany.
Okay.
Um, and so they used living trees, obviously, then dead trees, historical building material, and then for the oldest part, they used material from peat bogs and from river sediment. So that was wood that has been preserved underwater because it's been preserved in anoxic, so in conditions where oxygen cannot reach it. Without oxygen, also
Like it couldn't
decompose.
decompose,
Yeah,
or like
it
bacteria?
cannot decompose like the bacteria.
Mhm.
Thank you. Yeah, the bacteria and the fungi that decompose wood cannot live without oxygen. So if as long as the wood's underwater or without oxygen, it is preserved, and so it can be
Yeah.
preserved for 10,000 years, and that's how they
Ugh.
developed this longest tree ring chronology. But really, the you're right. We can compare it to ice cores and other climate proxies, lake sediments and
Mm.
corals, for instance. But really, the advantage that tree rings have over other climate proxies is that we have one data point every year, each and every year. So we can
Right.
look at the climate not just over long periods of time, but at very precise periods of time. And so we can look at these climate extremes, at heat waves, at wildfires, at storms, which is much harder to do if you don't have annual level data. You really need that
Mhm.
high, we call it high resolution, high temporal resolution to do that.
And so, you mentioned before these indicators that generally speaking, when we're talking about climate and when we're talking about the level of the ring, this like individual year, this very granular data, it's a function of poverty or abundance. So it's a function of the ring being nice and thick or skinny. Are there other kind of micro indications, like when you're looking down? You mentioned the frost rings too, but when you're looking at a cross section under the microscope, are there shape changes to the cells? Are there wiggly lines? Is there? I mean, what other kinds of things can you glean just from the morphology?
Yeah, so one important additional metric that we use, parameter that we use, is the density of the wood. So
Okay.
how, and that's really a function of how thick or thin the cell walls are of the wood
Hmm.
cells. And so it turns out that the density of the wood, especially of the late wood, so is very dependent on how warm or cold it is. So it is a very good proxy for temperature. So
Hmm.
in addition to just the width of the ring, there's the density of the wood, and then this is now something but this is a very active field of research, is really looking at what you're saying, looking at individual wood cells and seeing whether there's characteristics of the wood cells that we can use to look at additional climate of other conditions. But as you can imagine, that is very you need to take images of each ring at very high resolution and then automize the interpretation of those images. So it's very computing heavy
Okay.
application that's really only starting to pick up over, let's say, the last 5 years. So I think there's still a lot of information to be found there, but we're very actively working on that as a community.
It's fascinating that there's so much that you can glean from something that seems almost kind of nondescript. Something, I mean, we're so used to seeing the cross sections of trees. We see it in our furniture. We see it in doors. We see them on stumps when we're walking across lawns. And the fact that it contains so much, interesting information, and not just about the natural world, but in many ways about the kind of Anthropocene, about the human effects on the natural world.
Yep. Yeah. And also, I mean, and that's where the application of dendrochronology in archaeology and art history comes in. And that I find that so fascinating. It's not my field of expertise, but some of those discoveries I find just amazing, where you can date, for instance, when anything really that's made out of wood and that has enough rings in it, that can be a door or a beam from an archaeological site, or even a piece of charcoal or a musical instrument, and as long as it has enough rings in it, and as long
Hmm.
as you have a reference chronology that dates it to the present, we can provide a very exact date of when, let's say, that instrument was built, of when that painting that was painted
Oh,
on a wooden
wow.
oak panel, when that was painted. So it's, in a way, it's much more precise. For instance, I often get asked whether, oh, do you date material with radiocarbon dating? And it's actually the other way around. Like, it's much more precise than radiocarbon dating. And actually, radiocarbon dating as a method has been calibrated by radiocarbon dating, those very old bristlecone pines that I was talking about. So we're a much more precise method of dating than radiocarbon dating.
Oh,
In a,
that's amazing. And I think about like art history so much of like ancient art was painted on wood. You don't even really realize it sometimes. You're so used to looking at these images on your computer screen. But then when you're lucky enough to, I remember going to see, Hieronymus Bosch in real life and realize like, oh, these are altar doors or this is a
right,
table.
right,
Like this is not a
right.
canvas.
Right. And so it gets better because we can date the wooden material on which these paintings or music instruments were made, but because by now we have a network of more than 4,000 chronologies, and for some regions the network is even more dense than that. Um,
Hmm.
and because if you remember from the very start of our conversation, I was talking about how all trees that grow in the same region will show a similar pattern of wide and narrow rings throughout the
Hmm.
years. Because we now have such a wide network of tree ring chronologies, by comparing the chronology or the sequence of rings that you see, let's say in a wooden altar panel, by comparing that to chronologies from various regions, you can find the best fit, and in that way also figure out not just when the piece was made, but where the wood came from that it was made of.
Oh,
Um,
wow.
and so, for instance, a colleague of mine, I mean, she does really cool work. She is a shipwreck dendroarchaeologist.
Oh,
So,
wow.
yeah, so her job is to dive to shipwrecks to then take samples from the wood in those wrecks and then to use dendrochronology to find out when those ships were built and what the origin of the wood was. And there's so much you can find out about history, the history of wood use, the history um, of trade as well throughout the years.
Oh, that's fascinating. And so, in sitting down to actually write this book, was the intention from the very beginning to say, okay, I really want to write like a popular science book about the more kind of heady academic stuff that I do? Was it to kind of I don't know, broaden your own education so that you could talk to all of your
Yeah.
colleagues and look at all the cool ways that dendrochronology is being used?
Well, the original intention was the first. So I was very lucky. I've been very lucky. I was in 2017. I got a sabbatical from my university, so I was lucky in that way. And I really wanted to do something else, but just, continuing to write grants and write papers. I needed a break. I wanted to do something else. And so at the
Mm.
start of my sabbatical, I actually got an email from Tiffany, who's now my editor at Johns Hopkins University. I didn't know her before, so I got this email out of the blue asking me whether I was interested in writing a broad audience book about dendrochronology. And my first reaction was like, oh, surely that exists. It's such a easily accessible science, and there's so many great stories to tell about tree rings. Like, surely someone's written that book already. And then I started
Mhm.
thinking about it and realized, no, actually, I cannot think of a book like that. And I'm a dendrochronologist, so if it existed, if such a book existed, surely I would know about it. So it was from the get go the intention to write a broad audience book and to bring the many stories, science stories that we can tell with tree rings to bring them to a broader audience. But it's absolutely right what you said, that I learned so much through writing this book. There was so much that I didn't know that I'm a little embarrassed about, because my official title is professor in dendrochronology, and yet there's so much that I didn't know about my own field of research. It's been great. It's been a great learning experience for me as well.
Is it a big field? Like, is it one of, sometimes in the sciences, there are fields that are so big and so like branching that you can't possibly keep up with all the literature. And you kind of don't know most of the people. You go to conferences and there's thousands of people. And then there are fields where it's like, yeah, we kind of all know each other's names and we pretty
Yeah,
much know
yeah.
what everybody's up to. Which camp does it fall more into?
I would say more the latter.
Nice.
Our conferences are maybe, the World Tree Ring Conference is maybe 400 people, 500 people. So I wouldn't say that I know every dendrochronologist in the world at all, but I know a lot of them. And
Hmm.
in terms of keeping up with the field, there is a bit of I keep up with the field of dendroclimatology. Everything that's going on in the ecology sector, and that's really growing now as well, because how trees, their wood is made up of carbon, right? So trees, through photosynthesis, they take carbon out of the atmosphere and then store it in their wood. So they're a very important component for us to find a solution for anthropogenic climate change. And so there's a lot of research that's going on in that area. But it's growing so fast. There's so much happening that it's, for me, as someone coming from a slightly different perspective, that's a big field to try and keep on top of the literature.
Yeah, yeah, for sure. And do you find that there's a lot of kind of collaboration across, fields? Because I know that one thing that is really striking about your book is that it's not just this historical journey, but it's also like a geographical journey. Like, you've really
Right.
traveled the world to learn a lot of these things, and my assumption is that many of your colleagues are covering other areas at the same time.
Yeah, yeah. So per definition, it's an interdisciplinary field. Like, as I mentioned, tree rings
Mhm.
are being used for archaeology, for climatology, for ecology, and they're all interlinked, right? When we wanted to reconstruct the climate over the last 2,500 years in Central Europe, we needed to collaborate with archaeologists who had the archaeological material to give us those data, because there's not 2,500-year-old trees in Europe.
Mhm.
So you need to collaborate. And for instance, one of the topics I describe in my book in a few chapters is how past climate change has been a factor influencing human history. So the rise and fall of past civilizations. I'm a paleoclimatologist. Like, if I'm not the one to know everything about past human history. So if I want to do that kind of research, which I find very interesting, I need to collaborate with historians. Or
Yeah.
as a paleoclimatologist, it's the reason why we are studying the climate of the past is to get a better idea of what's happening now and how that's going to change in the future. But with our trees, we look at the past. We don't look at the future. If I want to make my results as applicable as possible to our future climate, I need to collaborate with climatologists and climate
Mhm.
modelers. But that's really what makes it such an exciting time to be a scientist, right? There's we know so much. There's so much data to build on. The field of dendrochronology is now almost a century old. So we've been collecting tree ring data from across the world as a community for almost a century. We're sitting on this mountain of data, and now we have all the computing power that we need to run all kinds of exciting analysis on them. So it's really that's another reason why I wanted to write this book. It's very exciting to be a scientist, and there's so much discoveries to be made that I wanted to share with the broader audience as well.
Ugh, I love that. And it's such an interesting field that I think a lot of people don't think about as a potential career option. It's like in the back of our mind, we have these ideas about trees and about, what they can tell us. But then we sometimes forget, like, oh, yeah, there are people who are studying this and who are learning really fascinating things about our life history from looking at these, basically, these artifacts. And of course, in many ways, being able to project and be able to develop an understanding of the future and some of the decisions that we can be making now to help protect that future. It all kind of comes together to tell this really beautiful story.
Yeah, I couldn't have said it better than you. I came into this career rather serendipitously. I don't think there's, as you mentioned, I don't think there's many people who grow up thinking that they'll want to be dendrochronologists when they, as a career when they grow up. But I'm very happy that I did. There's so many interesting angles to look at. It's so relevant for our future. And then, to be honest, the material that we work with, it's so beautiful. Looking at wood through a microscope, it's gorgeous. It's really, yeah. I'm very happy with my career choice.
Oh, I love that. I would think it's so inspiring and it's so important for people, especially, there are a fair amount of listeners to the show that are doing what they're doing and they have their career and they're enjoying their lives and more power to you. I'm so glad to hear it. And then there's a fair amount of people who are in high school or in college and trying to figure out what their path is going to be. And so I'm always really excited to hear about strong, interesting women who are answering really big questions in fields that maybe didn't necessarily seem realistic to a lot of people, which I guess raises the question, like, what did you study to get where you are? Were you, what departments did you find yourself in throughout your academic career?
Right. So maybe from my accent, you can hear that my mother tongue is Dutch. So I'm from Belgium originally. I got all of my education in Belgium, and my bachelor and master's degree are in environmental engineering. So I have an engineering
Oh,
background.
okay. Oh,
Um,
interesting.
and it
Not what I
was,
would have guessed.
yeah, right.
Yeah.
um, and it was during when picking a master's thesis topic that I ran into dendrochronology. So, and again, really serendipitously, I'd never heard of dendrochronology before, but I was looking for a topic for my master's thesis, and I really wanted to go abroad. And there was this one topic that was posted to study tree rings in Tanzania, and I really wanted to go to Tanzania. So I figured if tree rings bring me there, then I'll go and do that.
Hmm.
But then when I went to Tanzania, brought back samples, and then when I started looking at the wood through the microscope in the lab, that's when I really enjoyed doing that a lot. So I continued on to do a PhD from there on, still in environmental engineering. And after my PhD, finishing my PhD in Belgium, I moved to Penn State University for a postdoc, and that was in the geography department. So I
Okay.
think a lot of what we do, and many of my colleagues are in geography, physical geography. then there's obviously it depends a little bit on which of the three main pillars of dendrochronology that you're working on, whether it's climatology or ecology or archaeology. My archaeology colleagues are in archaeology or anthropology departments often.
Mhm.
Then my ecology colleagues are often in forestry or natural resources departments or geography or geosciences. Myself, at the moment, I'm now a professor at in the laboratory of clearing research, which is a department of its own. But we don't have a graduate degree as a
Okay.
department. So my grad students come in through either geosciences or the School of Natural Resources or hydrology and atmospheric sciences. So it really depends on, because it's such an interdisciplinary science, you can come at it from a lot of angles.
Right, because I'm sitting here assuming, and maybe it's because of my bias that I came up through um, the biology department at my school, and I saw a lot of plant biologists, and so my assumption was that like this was mostly going to be ecology, environmental science, or just like basic biochemistry or something like that, and people would
Right,
find themselves in this field that way. But it's really interesting how much of it is through this kind of like engineering background or even this geography background.
right, right. Yeah, and I think also, yeah, with the geography angle, as climate human interaction or human environment interactions are becoming more important and more people are studying it. I think that's where geography really comes in and really, combines these different angles well.
Right. Yeah, yeah, yeah. I mean, it makes perfect sense. It's just like it's science is so multidisciplinary now, and there's so many different ways to kind of meander yourself to the goal. That I mean, as you mentioned before, it's a really exciting time to be a scientist. I think it's also a really exciting time to be a developing scientist, like to be in academic science and learning about science because you have so many more options now
Yeah,
than you ever
yeah,
had before. And really you can pave your way however you want to get into the field that you like, which is really great.
yeah. I can't agree more. Yeah.
Oh, I love that. Well, gosh, Valerie, I feel like I've learned so much. I know that there's still so much more to learn, but as we're getting towards the end of our conversation, I was wondering, A, if there's anything we haven't covered yet that you would like to cover. And then after that, if at the very end you'd be willing to answer the final two questions that I ask all of my guests who join me on the show.
I think we covered a lot of ground, so I don't.
Right?
Yeah, yeah, it's been fun. So yeah, I think I'm ready for your final two questions. Sure.
Awesome. Okay, so these are pretty big picture questions, but I want you to answer them contextually in kind of whatever however they feel relevant to you. So the first question is, when you think about the future, and we could be talking about the future of your career, the future, something personal or something much bigger, like something more global. Number one, what is the thing that's really keeping you up the most at night? The thing that you're most kind of concerned about, maybe even, I don't know, pessimistic about? And then on the flip side of that, so we end on a positive note, what are you like genuinely looking forward to? What are you hopeful and optimistic for?
I think that's a fairly relatively straightforward questions to answer as a climatologist. So
Mhm.
climate change keeps me up at night. Mostly what not climate change per se, but climate change in a very densely populated world with a socioeconomic structure that we have. So that keeps me up. What is that? How how are we gonna handle that? And then
Mhm.
what gives me hope is that really we have a lot of the solutions in hand to get started right now. Right? We know what we need to do. We need to bring our carbon dioxide emissions down, and we need to find alternative sources, not just find, we need to apply alternative sources of energy use. So it's not that hard. We can do it.
Yeah.
So I'm hopeful that we can do it. And again, it's in addition to that, it's, as I mentioned, it's a great time to do science. There's so many things that we don't know yet that we're on the verge of finding out, both in terms of science and in terms of climate change solutions, that make me hopeful.
I love it. I mean, I think that it's not an uncommon answer. So that's good because I feel like even people working in other fields of science are obviously not just acutely aware, but incredibly concerned about the climate crisis. And so it's good to see that you don't have to be an expert to, I think, be concentrating on changes that we can be making on both an individual level, but even probably more importantly on a policy
Yeah.
and kind of governmental and corporate level. So that is good to hear, but it's also good to hear those sentiments coming from somebody who does this for a living. I think it's obviously an important message that all of us needed to hear. And I'd say the same for your new book. It's called Tree Story: The History of the World Written in Rings. Valerie, thank you so much for joining me today. I had an absolute blast.
Me too. Thanks. This was great, Cara. I really appreciate it.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.